Good morning. Last day of classes today. Usually I'm more sad than I am today because then I know you guys, but it's been kind of a weird term, so it's kind of nice to have the classes done, but also because it means that we'll have seen all the material, which I always find it's easier to study if I have kind of all the material that I've seen all the material already, and then I can kind of figure out what I need to work on. So that's always nice. I posted a practice final, okay? We do have another section to finish today, so we are gonna do some new material, and if there's time at the end, then I will go back and have a look at that practice final, but otherwise it's a good indication of what to expect for the final exam. Okay, so I have posted a practice final on WebAssign. Okay, it's the same length, it's the same types of questions as the final. Same length and types of questions as the final. Okay, for the final you have 3 hours to do it. So we have our final on Wednesday from 1 till 4. Okay, so you will have the full 3 hours to do it, including showing all your work and submitting all your work. Okay, so you do have to show all your work, and the order of the questions on the final will be different. Okay, and so the order of the questions on the final will be different. Okay. The reason I've done that, and you can probably figure out sort of what the order would be, because what I want to do is I want to have the work that I want to look at the most. So the stuff that we haven't had a test on yet is going to be at the front. And then stuff that I've already marked or that doesn't really need a lot of work is going to come towards the end. So it's going to come, so the order on the final is in order of how important the work that you show is, okay? So the order on the final, and maybe I'll do this in a different color. The order on the final will be in decreasing order of importance for showing the work. So the questions that don't need a lot of work, or that I don't really want to look at the work anymore because I know that you guys have mastered it because I've already marked it, those will be towards the end, and then the ones that I am really interested in looking at the work will be at the top. Okay, so you have to show some sort of work for all the questions, and you still have to submit all your work, just like the tests. But just maybe focus on and make sure that you show lots of work for those first kind of half of questions, and then if nothing else, just write down the answer that you pick in your work if there's no work involved. Okay. What else did I want to say about the final? You will have 3 hours to complete the WebAssign test. Complete the WebAssign test and upload your work to Moodle, just like the tests. And upload your work. I want it in order. Just, you guys have been really good about that, so it's not something that I have had a problem with in the past, but I do want to say that it should be in order. So and upload your work in order to Moodle. Okay. I'm also going to post an academic integrity quiz. And that's just to make sure that that you know what to avoid, right? You can't work with each other, you can't talk to each other. If any thought that you're putting on in your work isn't your own, then that's bad. Right, so anything like that, and it's just a quick Moodle quiz. I think it's 4 questions or something. So I'll send out an announcement for that. Sorry, I'm just gonna draw the blinds here. It's like crazy sunny. Just a second. There. Oh, that's better. It was getting hot. Sun on my face. Okay, it's nice, so I'm not complaining, but whew. Okay, so that's what I wanted to say. I saw that some of you have already tried the practice final, so I had posted a practice final. There's a different one now. It's not different, it's the same questions, but I just changed the order so that it was in the order of how we saw those topics. Okay, so from chapter 1 through, I guess, 6 is how they're appearing. Okay, so okay, I do have my eye on the chat. I haven't seen any questions. If you do have any questions about the final, let me know. But otherwise, let's do some review here. Okay. So section 5.3 was on trigonometric graphs. And I kind of cut right to it, right to what we need out of this section. And so let me just change. Okay, good. Which was this blurb here. And I'm pretty sure I said we were going to do 4 together. Okay, but let's just talk about, so the rest of the handout kind of builds up to this. So I did just jump in there, but we can go back and we can look and we can say, okay, well, we're going to talk about the amplitude, the period, and the horizontal shift of a sine and cosine curve. Okay, so what that means is the amplitude is the distance from the x-axis up to the highest point. Okay, so what we established last day is that sine and cosine are these cyclical functions, right? Because cosine is the x value around the unit circle, the y value is the sine, right? And so as we move a distance of 2 pi, right, we loop back to where we started, and then we go around again, and then we go around again. And so then we have a period of 2 pi, right? It takes a distance of 2 pi to repeat itself. And so that period, if we kind of flatten it out, you have to think of it as kind of stretching it out. The period then is how long does it take for basically to get around the unit circle, right? Or in general, how long does it take for this function to repeat itself? Now we can have sine and cosine curves, and sine and cosine, typically they just, well, not typically, always, they're just kind of forever, they keep going forever and ever and ever, and they're just kind of like wavy functions. Okay, so they don't have any asymptotes or anything, they just kind of keep going and going and going and going. And so, and the period is how long does it take for this thing to repeat itself, okay? by default, both sine and cosine have a period of 2 pi, right? The amplitude, by default, the amplitude is 1 because the highest value that we can get to, think about the unit circle, the highest value that we can get is 1, and the lowest value we can get is -1 if we're down at the bottom. Or if we're talking about cosine, right, then those are the x values. So then we're at +1 going to -1, and those are the largest values we can get to. So either way, we're stuck between 1 and -1. Just depends on where we're starting, right, depending on if we're at sine or cosine. So, oh yeah, and then we can incorporate a horizontal shift, right, just by bumping everything over either to the left or to the right, okay? And so how those are reflected in our function here, depending on if we're talking about a sine function or a cosine function, notice that if you have a look here, these look the same. It's just sine or cosine. So you'll want to match whichever one you have, right? If I give you a cosine function, then look here at the cosine one. But regardless, the amplitude is going to be the absolute value of A, right? So you need to find A. The period is going to be 2 pi divided by k. Notice in either situation, k is on the outside multiplying x, okay? So x is on its own. So if it's not on its own, you have to move all the coefficients of x outside, and that's going to be your k. And then minus, and that's important, right? If you have +4 here, then b must be -4. Right, so minus b, so the horizontal shift is b. Okay, and we did an example, I think we did the one in the notes actually, right? So find the amplitude, the horizontal shift, and the period of this graph here, or this function, and then we graphed it. We didn't graph it, we just looked at here, and of course, I'm not going to get you to graph anything because that's really hard, but I think if anything, you have to pick the right graph, of course. We've done lots of those before. So 3 is being multiplied outside, so that's our amplitude, which means that this thing is going to stretch up to a maximum value of 3, but also to a minimum value of -3. Right? So it's going to be stretched between 3 and -3. The period is 2 pi divided by 2, right? So now it's saying that, okay, over a distance of just pi, right? So we're squished together, we cover an entire cycle. And then minus b, so minus pi/4. So the phase shift is pi/4, meaning that everything is just bumped over pi/4 units. Okay, so we said we were going to do 40 together. Okay. And I'll tell you why I picked this one, because I want you to have kind of be able to keep an eye out. Oops. Okay. So we're going to do 40, and I picked 40 because, okay, so the reason is that I wanted something that had something being multiplied by x in here, right? Because you don't just have x minus b in here, you have something times x minus b, kind of a b, right? And so because there is a coefficient on x, okay? So this here is the reason that I picked it, okay? So Another one we could have picked, right? We could have picked just as well. It looks like this one would make us practice that as well, right? So that's another option, right? Maybe have a look, maybe try 39, right? 39 is also good. Is also good to practice. Okay. You don't need to worry about things like the 1/2 minus the function, right? So you don't have to worry about something like that. And notice that these ones all have x on its own already. So, nah, I don't think so. And then this one's a little tricky because the minus x is on the outside. So I picked 40 for a reason. 39 would be good practice as well. Okay. But notice that all the other ones just have x on its own. So they're a little bit easier than these two. Okay, and I'll show you why. So 40, let's write it out here. We have y equals 2 times the sine of 2 over 3x minus pi over 6. Okay. So what we want to do to find and we're asked to find the amplitude, the period, and the horizontal shift of the function, and then we're going to graph one complete period. We're going to use Desmos because you're on WebAssign, right? You just pick the right graph. So we're not actually graphing, but so we'll just use Desmos. Okay, so to find the amplitude, the period, and the phase shift, or the horizontal shift. Horizontal shift can be called phase shift, right? So just keep an eye out for that. Okay, so we want to match. I've got a sine function here. So I want to match the sine function that I've been given up here, right? So here, this is sine, which means I can just ignore the cosine one for now. They're the same, but just in case. So here, want to rewrite our function to match this. Okay. A key thing is that x has to be on its own, right? X must be on its own. Whereas here, right, I've got the 2 over 3 multiplying out front here. The important thing is that I can't just bump the 2 over 3 outside because that's not how multiplication works, right? I need to take it out of the pi over 6 as well, right? And so we need to factor out a common 2 over 3 from 2 over 3x minus pi over 6. Okay, so factoring it out from the 2 over 3 is fine, but then we need to think about, okay, well, what happens with the pi over 6? What I want to do is I want to divide out 2 over 3. So what this looks like is I get 2 over 3x minus pi over 6, and I want to divide it by 2 over 3. I can split this up. This is the same as, 2 over 3x divided by 2 over 3 minus pi over 6 divided by 2 over 3. I've written them with the slashes instead of the straight bar, but that's just to save space, and maybe I shouldn't do that. Maybe that's lazy. Okay, so I'm allowed to split this up because it's a common denominator. And what I'm going to see here is that I've got a fraction over a fraction, right? So I can flip and multiply. So what happens here is I get 2 over 3x times 3 over 2, which we expect to be 1, right? Because that's what we're forcing to happen. Okay, so that's no surprise. But then we get minus pi over 6 times 3 over 2. Okay. So canceling here, 3 over 3 and 2 over 2 cancel, so you just get x, okay? What that means is I can extract a 2 over 3 to the outside, right? And then here, right, 3 over 6 times 2 is 3 over 12, right? And so 3 pi over 12 is the same as pi over 4. So here, depends on how you want to do it, right? 3 and 6 can cancel, so then you have 2 times 2 here. And then, so this becomes 1 over 4. So therefore, we can rewrite, what was that original function? 2 sine 2 over 3 y equals 2 sine 2 over 3x minus pi over 6 as y equals 2 sine 2 over 3 times x minus pi over 4, because we've extracted this 2 over 3 from here, right? Because this becomes pi times 1, which is pi over 4. Okay. So now I have x on its own, and that's what's really, really important, is that x is on its own. So then whatever is left over here, this is the horizontal shift, okay, as long as it's minus that b. So what we have here is we have a is 2, and I'm just going to grab that, and maybe it's still here. Okay. So I'm just trying to match this, right? So a is 2, because we need a, k, and b to find the period, the horizontal shift, and the amplitude, right? And so a is 2, k is 2 over 3, and it looks like b, because it's x minus b, so b is pi over 4. So here k is 2 over 3, and b is pi over 4. So then what we have is the amplitude, and I'm going to write them kind of side by side here, because then I don't have to scroll around so much. So it's really just a matter of saving some space here. So the amplitude, and this is where it gets to be really important, is the amplitude is the absolute value of a, right? And the hardest one to keep track of is the period. The period is 2 pi over k. So we found k, and a lot of people just want to say, oh, k, 2 over 3, that's the period. No, 2 pi over 2 over 3 is the period. Okay, so that's really important, because that's the one that trips people up. Because the amplitude is basically going to be a, and the horizontal shift is basically b, right, depending on if it's adding or subtracting. And so this is the only tricky one that we have to pay attention to. Okay, so the amplitude is the absolute value of a, which is the absolute value of 2, which is just 2. Okay. The period is 2 pi over k, and that's supposed to be a k. Well, it still doesn't really look like a k, but that's okay. So the period is 2 pi over 2 divided by 3. here again, we have a fraction over a fraction, right? 2 pi over 1 over 2 over 3. I can flip the denominator and multiply. So, oops, I get 2 pi over 1 times 3 over 2. So I have a period of 3 pi, meaning that it's going to take a distance of 3 pi. So now it's kind of stretched out in comparison to what we're used to, right? We usually take a distance of 2 pi to do a complete cycle, but now we're taking 3 pi to complete a full cycle. So now the period here is 3 pi. And finally, the horizontal shift can also be called the phase shift, is B, okay? Because I'm subtracting here, it is just the pi over 4, meaning it's going to shift over by pi over 4 to the right, okay? Which is pi over 4. If this was plus pi over 4, right, then our B would be negative pi over 4, meaning we have to shift it to the left pi over 4, right? But because we're subtracting the pi over 4 here, we're okay. That is our B. Good. Any questions about those graphs? Oh, before I go into Desmos and just graph this really kind of briefly here. I'm going to do 2 graphs, okay? The first one, I'm going to graph the original function, and then I'm going to graph my new version of the function because they should be the same, right? So that's one way that I can check to make sure that I have the right factor in here, is to make sure that they're the same graph. Okay, so let's go to Desmos and do that. Okay, I have 2 times the sine, which should be in the functions. Yeah, the sine of 2 over 3. And just make sure that you write it out the way it appears in the question, times x, minus pi, which is also, it's on the calculator here in the lower right hand or left hand corner, kind of over to the right, there's the pi button. Okay, pi divided by 6, and then close that bracket. Okay. So, okay, let's see here. That's what the function that we're looking at looks like, right? And so just a couple of things here. It has moved over by pi over 4, so that's a good start. The highest value is at 2, right? The highest y value is 2, so it has an amplitude of 2. This goes down to -2. And it goes from pi over 4, right? And then it takes a full cycle to 13 pi over 4. So it's gone a distance of 12 pi over 4, which 12 divided by 4 is 3, right? So 3 pi, that is the full distance. So it looks like everything that we found checks out. Okay, what I want to do is I also want to graph our factored version just to make sure that it overlaps the one that we were supposed to have, just to make sure that they're the same. So I need 2 times the sine of 2 over 3, and then I'm going to put the brackets here, times x minus pi over 4, and then end bracket, end bracket. Hey, looks good, right? Looks like they overlap, so they're the same. So that is a really good sign, because that means that this 2 over 3 that we extracted, we did it properly, right? So you can always check your work. And what I'm going to do is I'm going to just have all those. And oh, I watched a YouTube video on how to use my iPad better, I guess. And they taught me that I can just take a screenshot like that. How cool is that? Just drag from the bottom right hand corner. Okay, cool for me. I don't know, it doesn't matter to you. I think it's cool. Okay. So I draw both the original. Hey, how come it didn't keep the... Thanks, Ishpreet. How come it didn't keep the little things that I had on there? What the heck? They're gone. I wanted those points. Is it when I take the screenshot like this? No. There, it kept them. Okay, let's see here. Delete. Taha. I don't know why it didn't. I wanted these little buttons. I don't know. So I draw both the original and the factored graph, and I'll kind of put factored in quotes, and the factored graph to make sure that they overlap, because that means that I did it right. Factored graph to make sure they overlap. Because that means I did it right. Right? And we can check things like, okay, the amplitude is 2, we're going to a height of 2. So here we can check our work, right? And say that here, this distance, the amplitude is 2. The period is this distance here. So the distance between pi over 4 and 3 pi, the period, 13 pi over 4 minus pi over 4 is 12 pi over 4, which is 3 pi. Right, 12 over 4 is 3. Okay, so good thing, looks good so far. And then we've got that phase shift, right? From 0 to pi over 4. This here is the horizontal shift. Is pi over 4. I do want to say it's because this is a sine function that the horizontal shift is pi over 4. Because what if this was a cosine function? Then what would the horizontal shift be? Well, horizontal shift is how far off of the y-axis from the original position did it move. Sine starts here at 0, 0. So that's why we follow that 0, 0 point. It moved over to pi over 4. What if this was a shifted cosine function? Well, cosine starts here at on the y-axis up above, right? So at the amplitude. So it would have started here at 0, 2, and then we've shifted over by a distance of pi, right? So if this was a cosine function, the horizontal shift would have been pi, right? So it depends on which function we're talking about, but we treat them both the same way. And so here we were able to check our work, right? And so we can use the graph to check our work. And because I feel like I haven't used a lot of these yet, and of course it's really important to use stickers. No, it's not. I do encourage you to check your work, right? Whatever you can do to make sure that what you're saying makes sense, then that's a good thing. Okay, and you are allowed to use Desmos, of course, on the final exam. But if you're using Desmos, you should say, I use Desmos to find these numbers, okay? And I use Desmos, just tell me when you're using Desmos, and that's fine, that's a good thing. Okay. Can you believe it? Are you ready for your last section? Can do it. So the last thing that we need to talk about is inverse trig functions. Okay, so we've talked about the inverse of functions before, right? Just plain old inverses, how did we find the inverse function, and so on and so forth. And then we talked about the logarithmic function being the inverse of an exponential function. And now we're going to talk about the inverse of trig functions. Remember, one key thing for to have an inverse is that it has to be one-to-one, right? Meaning that if I draw a horizontal line, it can only cross the graph once. And if you have a look at this graph, well, it looks like I'm going to cross this graph at any point, regardless of where I draw this line. At any point, I'm going to cross the line more than once. In fact, an infinite number of times, because it keeps going forever and ever and ever and ever. So we're going to tackle that first, and then we're going to talk about the inverse functions. Okay, so section 6.4 is called the inverse trigonometric functions. And right triangles. Okay. So recall, in order for a function to be invertible, right, have an inverse. So in order for a function to be invertible, which is really just saying have an inverse, it has to be one-to-one. It has to be one-to-one, which we check graphically. We can check it by using the horizontal line test, right? We didn't go into it. We can prove it mathematically as well, but I'll leave that for calculus maybe if you need it then. It's pretty fun to do, but don't worry about it. Okay, so we can check this graphically. Using the horizontal line test. Horizontal line test. Okay. I'm going to go back and I'm going to grab the graphs for sine and cosine, because whenever I draw sine and cosine, they kind of go and get smaller and smaller, which isn't true. They stay the same width and height. So here, right, if I bring this in, so this is sine, and then I'll also bring in cosine, why not? Also because it's good to know what these two look like compared to each other. Okay, so they have some really similar properties, but I'll highlight that this is sine and this is cosine. Remember, sine starts at 0, 0, unless there's been a horizontal shift, that's fine. But in general, sine starts here at 0, 0, and cosine starts up top here at 0, 1. Okay. How I remember them, if I have them on the same graph, right? So let's say if I'm going to just trace this here. Can't actually see where my pen is there. If I put these on an overlapping graph like this, right? Then what happens is, so here, now this is the cosine of t. The cosine starts up here, right, at 0, 1. So, and then this is the sine. They're appearing in alphabetical order, right? And so C comes before S, and that's how I remember where they are, right? But you can also think about the unit circle, right? Cosine is the x value, and you start on the positive x-axis where x is 1, y is 0, right? There's lots of different ways that you can remember this. Okay? But regardless, right? If we're talking about the cosine or the sine, when I draw a horizontal line test here, any point, right? Neither of these functions pass the horizontal line test. Because sine and cosine both keep going to infinity, negative infinity, forever, and they have this wavy activity all the way along, right? And so if I try to draw a horizontal line here, I can't do that, right? And so neither of these functions, as they are, pass the horizontal line test. So what we do is we restrict the domain for both sine and cosine. Okay. So to find the inverse of sine and cosine, we restrict the domain until they pass the horizontal line test. And we restrict the domains for sine different from what we do for cosine. Okay, so to find the inverse of sine and cosine, we restrict the domain until they are 1-to-1. Right, so what we do is we just say, okay, well, how about the inverse is only working on this small little section? Okay? And so here in the notes, the 6.4 notes, I'm going to grab this guy. Uh-oh. There. The sine, cosine, and tangent functions. Remember, tangent is just sine over cosine. And so we can talk about the tangent as well, okay? And it's just these three that we're going to be concerned with. Really, we're not going to need to worry about any others, okay? So for now, let's just focus on these inverse functions. That's plenty. So we restrict the domains. The domain for sine, we restrict it to be -π/2 to π/2, okay? And notice that here, this is inverse sine, but the sine, so in order here, the domain for sine, we restrict it to be between -π/2 to π/2. So what does that look like? well, let me just grab this here, copy. And I'm just gonna delete this here, okay. So negative pi over 2 is going to be at this point here, right? Negative pi over 2 until pi over 2. Pi over 2 is here, right? If this is pi, then halfway would be pi over 2. Right? So what we're saying is we're restricting and saying, well, if we're only looking at this little curve, well, that passes the horizontal line test, right? And then what we could have done, we could have restricted it from pi over 2 to 3 pi over 2, okay? But that's not really something that we want to do because we want to hang out around the origin, right? And so we want to keep it as tight around the origin as we can. So that's why we pick from negative pi over 2 to pi over 2. We still see the full range of y values, but no repeating y values. Okay, so we restrict the domain for sine. We restrict the domain for sine to negative pi over 2 to pi over 2. Oh, I should use the same. Okay. In terms of the unit circle, right, that means that sine is looking from negative pi over 2, right? So that's the kind of dropping from the positive x-axis down to the y-axis, and then up to pi over 2. So thinking about the unit circle, and I know this is kind of like, but I just want to show you so that you have them. Available. Okay. So pi over 2 is going to here, pi over 2 and negative pi over 2. Okay. So these are all the possible values for the inverse of sine, right? So this is for sine. We're restricted to this half of the unit circle, okay? Because here we repeat root 3 over 2, root 3 over 2, we've already seen it. So whatever we need to say at root 3 over 2, we can say at pi over 3. You'll see what I mean in a second here. So we can do the same thing for cosine. Copy. But cosine is restricted to 0 to pi, okay? And then the tangent, just to mention, is going to go from negative pi over 2 to pi over 2, but not including these endpoints, okay? So 0 to pi, 0 to pi. That's where we restrict the cosine function. So we restrict, and notice again, we see the full range of output values, but no repeating output values. And so there on 0 to, from 0 to pi, it is 1 to 1. So we restrict the domain for cosine to 0 to pi. Okay. And on that little blip, it's 1 to 1. On the unit circle, 0 to pi is from 0 radians, to pi, which is this top half circle, right? And so the output values, or the angles that we can have in cosine or inverse cosine, is going to be different from the angles that we can have in sine, okay? So we're going to be restricted to the top half of the circle for cosine. Oops, from 0 to pi means that this is where we're restricted to for cosine. And did I write anything? No. Okay. So this is for cosine. Okay. This is for sine and tangent, but tangent excludes these endpoints, okay, because we can't divide by 0. Here the cosine is 0, right? And so we can't divide by 0, but tangent excludes the endpoints. Okay. Okay, so let's talk about this little guy here. And okay, so we restrict the domain, fine, okay. Remember what we said about the inverse of a function? The domain of the inverse becomes is the range of the original function, and the range of the original function is the domain of the inverse. I don't think I said that right. Anyways, they swap. So the inverse sine, which we denote by sine to the -1, and it's really, really important that you don't think that sine to the -1 is 1 over sine. Okay, so one thing that I will say is that note, I'll do it in bright pink here, note sine to the -1 is the inverse sine function. Okay, it is not sine to the -1 is not 1 over sine. Okay, that's really important. And so the inverse sine function is something else, and most calculators, in fact, I'm going to say all scientific calculators, even kind of basic scientific calculators, will have inverse sine, cosine, and tangent buttons. Okay, so all scientific calculators will have sine inverse, cos inverse, and tan inverse buttons. Okay, so they will have all those buttons. Okay, and just a note that sometimes, especially if you're typing, right? If you're typing, you don't want to do sine to the power of -1 because that's annoying. So if we're kind of typing quickly, then sometimes what we'll say is that we'll say arc sine instead of sine to the -1. So that's just something to keep in mind, right? When I say arc sine, arc cosine, or arc tangent, what I mean is the inverse, and it's really just to not have to type out the power of -1, right? So that's just a quick note. Okay. So what does this mean? All right, how do we use these inverse functions? First, let's talk about what the inverse means, and we'll go from there. Okay, so how the inverse works is you can kind of float it around, right? So the inverse sine of x, if it equals y, you can kind of float this sign. You can kind of, in my mind, I do kind of divide it over, right? But when I move it over here, it becomes just the sine of y. Right, so here, this is equivalent to saying the sine of y equals x. So you can move that sign around. Okay, so then the cosine of y equals x, you can rewrite it as the inverse cosine, so just move it over, of x equals y. Okay. So, okay, what does this look like? I think we're gonna jump right into kind of, it looks like a really terrible question, okay? But it's not. Okay, so I'll show you one and we'll break it down and we'll talk about it. But what I wanna do is, and the solution is in the handout, but I just wanna walk you through it. Also, oh, oops, hey, I didn't copy it. Also because I don't have a lot of examples or problems from this section, so you should be able to do all of them, right? Because you need to practice. I wanted to focus your attention on some very specific problems, okay? At first glance, this looks absolutely terrible. In fact, I'll blow it up even more, okay? So at first glance, this looks like I'll never be able to solve that. Who knows, right? And so here, this looks hard to solve. Oh, okay. But don't worry, okay? What we do is we're gonna say, okay, so I've got an inverse here. I'm gonna focus on that inverse. Remember, if I take the cosine of something is always of an angle, right? So remember, we take the cosine, oops. We take the cosine of an angle, right? That's always true, right? Because the cosine, remember, if we think about our unit circle, right, the cosine is the x value as we move around the unit circle. But how do we move around? We move around by giving it some angle, right? So whenever we take the cosine, it's of some angle. So what we're going to start by saying is we're going to let this mess inside here be denoted by just a theta, some angle, right? We use theta to, and theta is just a circle or an O with a line through it, right? So theta to denote an angle. So step one here, step one is you're going to say let theta be everything inside the sine inverse of 3/5. Okay. So you take a step back and you say, okay, I'm going to let theta be everything inside, right? Because I'm eventually going to take the cosine of some angle. I just don't know what it is, right? And then that's going to give me an answer. So, okay, so then I swap this out for theta. Now, if we go back and we look at, okay, so I've got the sine inverse of 3/5 equals theta. What I can do, right, I've got the sine inverse of 3/5 equals theta. So what does that mean? It means that sine theta, right, shifting that sign over, sine theta is equal to 3 over 5. So I'm going to copy this so that we can make this connection here. So this sine theta, right, just like this sine theta floated onto this y, and that's kind of how I think about it to make this sine y. Now I'm going to do the same thing, right? I'm going to float this sine inverse onto this theta. So what we find is that sine theta is 3 over 5. Now, so make sure that you can float this sine inverse onto the theta, which makes more sense, right? The sine of some angle, which we just said, hey, I want to eventually find the cosine of that same theta, right? That theta hasn't changed. But now what I know is that sine of theta is 3 over 5. Okay. I also know that sine theta is from SOHCAHTOA, right? I can develop this right triangle. So we also know, and maybe I should use a different color here, maybe green. We also know from SOHCAHTOA that we can translate sine theta into a right triangle. That we can translate sine theta into a right triangle. Now, I don't spend any time, I just always draw the same right triangle. I don't try to bother making a length of 3 and a length of 5. I'm not going to worry about that. I'm just going to draw a general right triangle, which might look like this, right? This is a right triangle. It does not matter if you put theta. Remember, theta is going to be one of these two angles, right? So you have two options for theta. I always end up putting theta down here because it's easier for me to look at, right? And so here, if I put theta down here, right, then once I pick an angle for theta, right, if it's here or if it's in this top angle, if you prefer that, if that's easier for you to look at, right, but depending on where you put this angle, that's going to determine which side is the opposite, right? In this case, the opposite is on this side. So in this case, I've got the opposite. The adjacent side to this is here, and the hypotenuse is here, right? From theta. So it depends on where you put theta. But then the theta, the opposite, adjacent, and the hypotenuse. So if I know that sine theta is 3 over 5, well, that's the same as the opposite over hypotenuse. Okay. So then this 3 must go here, and this 5 must go here. If I have 2 of the 3 sides, I can easily find the missing side, right? And that's a good place to start. It doesn't really matter what you have to do next. It's just nice to have all 3 sides because then you can generate any trigonometric function that you want. And so since we know, and maybe what I'll do is I'll just put a little question mark here. Since we know the length of 3 sides, we can solve for of 2 sides. I don't know why I said 3. We can solve for the third, that's what I wanted to erase. We can solve for the third side. Which is a squared plus b squared equals c squared. C is always a hypotenuse, right? And so what we have is we have 3 squared plus b squared equals 5 squared. So 9 plus b squared equals 25. 25 minus 9 is 16. So b squared is 16. So b is the plus minus root of 16. I can't have a negative length, right? But can't have a negative length. So b must be 4. Okay. And that's what I take up here. Okay. So, oh, I forgot to give you guys a break, but how about this? We just finish the section and then we finish a little bit early. How about that? Because we're pretty much done. I want to do one more example and then we'll be done. You can do it. So now we have, this triangle, right? We have theta here, and we had 3, 5, and 4. Okay. And remember from before, right? We want to find the cosine of sine inverse of 3 over 5, I want to say. Yeah, 3 over 5. But we replace this with theta equals sine inverse of 3 over 5. Right, so then we want to find the cosine of theta. And now, all of a sudden, because I have this triangle, notice that this is the same theta, right? So now, because I want to find the cosine of theta, well, the cosine of theta from the triangle, the cosine is the adjacent over the hypotenuse. Now we can use the triangle to find the cosine of theta, which is the adjacent over the hypotenuse, right? The adjacent now is 4, and the hypotenuse is still 5. Therefore, the cosine of sine inverse of 3 over 5, which is what we wanted to find, ultimately becomes 4 over 5. Whee! So it looks really hard to solve, but if you remember this one, and you know what I did? I said step 1, and then I never gave you a step 2. So how about I fill that in? Step 2 is to map out the triangle. Step 3 is going to be find the missing side. And then step 4 is to put it all together. I should have remembered I was doing steps here. Okay. Okay, good. So So as long as you remember SOHCAHTOA and how to construct this triangle, right, the Pythagorean theorem, a squared plus b squared equals c squared, then you'll be able to solve these, no problem. Let's see here. I want to do, I want to do just one more. Okay. So I want to do, maybe I'll leave this one to you. A heads up that there is, I can't remember where it is, and I keep meaning to fix it, but, well, I can't fix it, but edit it. In the solutions, there is a typo in one of the solutions. So if you come across that, if you're working through these problems, and I am pretty sure that it's this one. So maybe what we'll do is we'll work through this one because I'm pretty sure that there's a typo in the solutions. Copy. And I don't want you to have to worry about that. Okay. I'll do it here. So again, similar situation, right? So sine of the inverse cosine of 5 over 13. Here it even holds your hand, right, and says, okay, we're going to let theta be the cosine, so whatever's inside here. And then we're going to complete this triangle, and then we're going to be able to find the sine of this thing. So if you have the cosine, the inverse cosine of 5 over 13, so we have theta is the cosine, the inverse cosine of 5 over 13, which means that the cosine of theta is 5 over 13. We have theta here. The cosine is what? Adjacent over hypotenuse. So that means that this is 5 and this is 13. We can find this missing piece using the Pythagorean theorem, right? And so 5 squared plus, and maybe I should write out the whole formula, a squared plus b squared equals c squared. So 5 squared plus b squared equals 13 squared. So b squared is 13 squared is 169 minus 25 is 144. So b is the square root of 144, which is 12, ignoring the negative because it can't be negative. So then here, so now if I have to find the sine, sine is the opposite over the hypotenuse, and so it's going to be 12 over 13. And you know what? I'm just going to go check the solutions really quickly just to see if this was the one that was wrong. 6.4 solutions. It's not. Maybe it's this one. The cosine of sine inverse. Maybe I removed it already. Anyways, there might be one with a typo in the solutions and I don't remember which one, and I'm really sorry about that. All right. We'll do one more example of this because I want you to be really, really good and feeling good about these. And then you'll be all done for the semester. How about that? So we'll do one more example. Last example of the term. Can you believe it? And then you're going to be free as a bird. Well, besides the final, I guess. Okay. So remember that once you have the triangle laid out, you can use that triangle to find any angle, right? Or any trigonometric function, secant, cosecant, tangent, cotangent, just by remembering from, I think, 5.2, maybe it's 6.2? Just want to remember which one, and I'll grab it for you. Yeah. So just to, as a reminder, right, from section 6.2, from section 6.2. Once you have the triangle, right, you can easily construct even the cosecant, the secant, the cotangent, right, which you have to use here, right? Cosine, cosecant, tangent, cotangent, secant, cosine, cosine, right? And then so you use the inside to develop the triangle, and then you can use the outside function, but the outside function just takes the triangle on the opposite, adjacent, and the hypotenuse. So let's see here. I want to do number 30 because 30 uses the inverse tan, right, which we haven't really used yet. We've been using sine and cosine. So let's do 30 together. And the cosine of tan inverse of 4/3. Okay. And maybe I'll put this on its own page here. First thing I'm going to do is let theta be this. Let theta be tan inverse of 4/3. Okay. What does that mean? Well, it means that I can float this tan inverse over onto the theta, right? So then tan theta is 4/3, which I can use to develop the triangle, right? Like I said, I always put theta down here because I just think it's a nice, nice way to start. So katoa, right? Tangent is the opposite over adjacent. So I have the opposite is 4 and the adjacent is 3. Oops. I have to use the Pythagorean theorem to solve for this value here. So a squared plus b squared equals c squared. Now I have 3 squared plus 4 squared equals c squared. So I have 9 plus 16 is c squared. So c must be square root of 25, which is 5. Maybe I'll do it. Okay. So then, now I need to take the cosine of this theta, but that's easy enough to do, right? Because, well, I want to find the cosine of this, which is just the adjacent over the hypotenuse. And so therefore, the cosine of the tan inverse of 4/3 is 3/5. And that's it. I'm going to try to do this on Desmos. I haven't checked it. It should work. But what you can do, and what I want to show you, is just finding these inverse sine functions with your calculator. Now, it's really important that you're in radian mode. So notice here, it's got the degree toggle. And then if you click it, it goes to radian. So here it's showing that you're in radian mode. So what we want to do is just build up this function. I want the cosine of tan inverse of, shoot, I can't remember, 4/3. 4 divided by 3. Which is 0.6. Or if you click the little box over a box, it'll show you as a fraction, which is 3/5. Right, so here, I'm going to copy that into our and crop it. We can check our work. In Desmos. Right, so one thing that I need you to make sure is must be in radian mode. And then you can hit this button here. Click this to get the exact answer of 3/5. Which matches what we have. Okay. Okay. That's it. You did it. Now, the end. Only because I've got a page break here, I can't do anything else. But let's see if I have an appropriate sticker. Whee! You did it. Yay. So kind of a weird section, but it takes these really hard problems and makes them pretty easy to deal with. So if you have any questions, let me know. Otherwise, I'll see you for the final exam. And it's been my pleasure having you this term, and I hope you've had some fun. I know it's math, so but thanks for being with me, and I've had fun. All right.